Good afternoon, everyone. Thank you so much for joining us today for our Civica Data Science Seminar series on this International Women's Day. I just want to tell you a couple of the house rules. So you are all muted, or like we ask you to mute yourself if you're not muted during the seminar, and the Zoom call is being recorded. You all should have got notification that the Zoom call is being recorded. So if you do want to interact in the Q&A section, when we will open the Q&A section and you will unmute yourself or like turn your camera on, you're automatically agreeing for your voice and your image being recorded. So that's just a quick note. And I'm extremely happy to introduce Dr. Erica Thompson. It's a person who's part of the Data Science Seminar series a host team. And we're very happy to have her at our seminar today. She's a Senior Policy Fellow in Ethics of Modeling and Simulation at the LSE Data Science Institute. Erica's research is centered around the use of mathematical and computational models to inform real-world decision-making. And today, Erica is going to present her just recently published book, Escape from Model Land. We're really happy to have her today. And Erica, the floor is yours, and you can share your screen now. And yeah, thank you, everyone.
Fantastic. Thank you, Olga. It's good to be here. I'll just share my screen. So hopefully now you can see that. Great. So I'm going to talk to you today about my new book, which is called Escape from Model Land. And it's about how we get out of model land, which is where we are when we're sort of inside the computer or inside our model or inside the system of equations that we might have written to describe the real world, how we get out of model land and make statements that are genuinely relevant to the real world and that can help us to make better decisions than we would have done without that information. So I'm going to try to talk with more of a data science flavor today to talk about hopefully things that are relevant for this kind of audience, but with a focus on the big picture, really thinking about how we make sure that we are answering the right kind of questions when we take our data and we try to use it to construct a model and think about influencing the real world. Okay, so I thought I'd start, quite basic by discussing how we get confidence in our models. So if you think about the phone in your pocket, you pick it up and you want to know what the weather's going to be like tomorrow. I think it might snow in London tomorrow, actually. So I don't know what it's like where you are, but you pick it up and you look at the forecast and you would like to make a decision based on that. Maybe you want to decide how to get to work or whether to take an umbrella or whether to hold an event. But how do you know whether that forecast is any good? How do you know whether it's going to be reliable? Well, you probably have some degree of experience, right? So you have consulted this weather forecast on many occasions and you have found that it is typically maybe reasonably good. Maybe you're a bit skeptical about it. Maybe you take a few different forecasts and sort of triangulate them a bit. But you have experience and you bring that to your interpretation of how good you think this forecast is going to be. And probably the forecast provider also has some kind of statistics. And so you can put that together over time. If we were doing a study of it, you could collect that data more systematically, and you could say on what percentage of occasions, for example, if sun was forecast or rain was forecast with a certain probability, how often does that actually happen in practice? And so you can build up a statistical picture of when it's likely to be right and when it's likely to be less confident or less accurate. And then you also make informed judgments about the quality of the model. So you can say it's not just because of my prior experience, it's also because I trust the UK Met Office, for example, or it's because I think that this model is based on fundamental physical laws and physical processes in which I have confidence. I expect them to continue to be valid in the future, and therefore I have some degree of expectation that this model is doing something sensible and not something crazy. So there are different ways of generating confidence in forecasts and confidence in the model that produced that forecast. But there are different kinds of forecasts and there are different kinds of models. And I want to distinguish here between, not a binary, but a spectrum of different kinds of forecasts. And on one end of that spectrum, on the left of this picture, are forecasts that are more like the weather, or they're based on the laws of physics. So these are forecasts where we expect that tomorrow is not fundamentally different from today, where we have a lot of data that we can use to evaluate the performance of the model. We can do that continuously. We can keep checking. We get more out of sample data every day out of our weather forecasts, and every day that gets used and fed back into improving the quality of the model. And so what that means is that our uncertainty is generically, our uncertainty is quantifiable because our uncertainty is measurement error, and it's uncertainties based on the limitations of the data that we've collected. It's not uncertainty that goes deeper than that. So those on the left-hand side of this diagram are situations that I would call essentially interpolatory, where the models that we're making are basically interpolatory and they are very much data-driven. And then at the other end of the spectrum is models which I would call essentially extrapolatory. So those are ones where for example, the underlying conditions might be changing in ways that are not fully understood. So that could be the climate, for example. So that's something that I have worked on quite a lot in the past, is thinking about models of weather and models of climate. And one of the problems with forecasting the climate is that even though obviously we expect the laws of physics to remain the same in the future, we don't know that the calibration of our models that we have done based on observations of 20th century climate, we don't necessarily know that those will be the appropriate parameterizations and model representations in a climate which is actually quite radically different, as we're expecting for the end of this century. And so that means that our confidence is not fully data-driven. Our confidence is based more on these other aspects of sort of expecting the model quality to be good. So we are expecting, for example, that the laws of physics will remain the same, and we maybe take multiple models, we try to make different models, and we have to make expert judgments about the degree to which we expect the models to be good in future, the degree to which we expect that past performance is indicative of future success. So with the data-driven models on the left-hand side, we are making an expert judgment that past performance is indicative of future success with high confidence. And on the right-hand side, where we are more extrapolatory, we say past performance hopefully is useful. Obviously we wouldn't trust a model that was extremely bad in the past, but that past performance is not a good guarantee of future success, and that we have to incorporate this expert judgment. So I'm hoping that makes sense to you all, and that you can sort of see the distinction that I'm making between these two types of models, and also that there is a spectrum, and that in most cases we'll be somewhere in the middle. So the highly data-driven approaches, maybe yes, we're at the far left-hand side, and the highly extrapolatory or maybe social systems will be at the far right-hand side. But in general, we're somewhere in the middle, and we have to do a bit of both, a bit of everything. So just to give a few examples, I think, because that might be helpful also in situating this. In that interpolatory category, the left-hand side, I would imagine the sort of things that quite a lot of you might be working on. So, for example, the large language models, depending on what you're using them for. I mean, if you're using them to do something that is going beyond the training set, they are not going to be able to construct, imaginative responses to solutions, sort of human scale things, but they are going to be extremely good at summarizing data for which we have strong data-driven representations of the relationship between different words and the construction of different sentences. So weather forecasting is in this category, the basic laws of physics. If you think about sort of industrial and commercial uses, mechanical testing, optimization of manufacturing, transport timetabling, online marketing, these are sorts of things where we can expect to have lots of data, and we expect that yesterday's data are relevant for tomorrow's forecast. And this is where AI and machine learning approaches can be extremely valuable, because they can help us to find and use those patterns that are in the data that we wouldn't necessarily be able to get if we were coming in as a human and imposing our own expectations of the structure on it. We can find the less obvious structures in these data. And then at the other end, and this is probably more the focus of my work, but I'm interested in both ends of this spectrum. In the extrapolatory category, there are what I sort of think of as large-scale prediction questions, and these are things like climate change impacts, energy policy. The pandemic is an interesting example, because I think on the maybe 1 to 2 week time scale, we have something which is effectively more interpolatory and data-driven. And because the outcomes over the next 2 to 3 weeks are baked into infections that have already happened. And so in principle, it's possible to measure that and to understand it and to estimate it. But if we're looking at the pandemic, say on a 6-month timescale, and we want to know how it will evolve, how the numbers of infections will change over 6 months, well, that's something that we in principle cannot possibly get out of past data, because it is also a function of public attitudes. It's a function of policies and government decisions. It's a function of social behaviors, which are inherently not really predictable, or potentially predictable in some ways, but always subject to the radical uncertainty that something might happen that just changes the way people think about things. Then there's things like financial markets, bank and insurance regulation is something that I've been looking at, security, cybersecurity, or the use of new technologies. So, a huge range. And obviously, you could think of many, many more examples in both of these categories. And perhaps we can come back in the discussion if anyone has any ideas about that. But maybe a point to sort of stress here is that if we're over at this end of the spectrum, we cannot expect purely data-driven approaches to give us an answer. Artificial intelligence essentially always needs some kind of help with extrapolatory questions, because it requires these expert judgments and it requires these assumptions to be built in. Now, you can do that. It doesn't mean that you can't attack these problems with AI and machine learning approaches, but it means that we have to be careful about how we being transparent about how we embed value judgments that are going to be necessary, and how we approach the question of making these expert judgments. Okay, so thinking then a bit more about evaluation. So how we would like it to work, and hopefully many of you are in this lucky category. If you're on the left-hand end of the spectrum, you're in the interpolatory data-driven regime, then you can sort of proceed with model evaluation in the textbook way. You can say, I'm going to gather lots of data, I'll keep some back for testing, or I'll plan to collect some more for testing. I train the model using the data, but also using my understanding of the system. You find out that the model is good, but it's not perfect, because it never is, because it can't be, because all models are wrong, as a famous statistician once said. And then you use your held out data to evaluate the performance of the model on what you're interested in. Hopefully, you can use that to improve the model, but even if you can't use it to improve the model, at least you have it to understand when you expect to have confidence and when you expect not to have confidence. None of this implies that the model is perfect, but you don't need a perfect model. You only need to know when it's reliable and when it's not reliable. So then hopefully, if you're on a short time scale, you'll be gathering new out of sample data. And so you can keep doing this process, and you'll be able to generate ranges which are actionable in terms of being able to use them to inform decision support. And hopefully you will be confident about those uncertainty ranges. You'll be confident that if you generate a 90% confidence interval for the target of your prediction, that on 90% of occasions, the actual outturn will be within your 90% confidence interval. And on the other 10% of occasions, of course, it will be outside that interval, but that was what you expected, so that's okay. And if you have that, then you have something which is genuinely useful because you understand and you're confident in it. But this isn't always the case. I mean, maybe the other thing to say here is that when you are doing this, even if you're in this happy situation where we have lots of data, we can use it, and the model is evaluatable, we are also introducing expert judgment. So I'll just say very briefly, sort of illustrate how that happens. And again, this is something I'd be interested to hear feedback on from the audience at the end as to whether this is something you consider. So here's a little sketch of a model. You know, you have inputs and you have some kind of output. I've drawn this in 2 dimensions, but of course there could be hundreds or thousands of dimensions. It's just harder to draw that on a computer screen. And the model, the red line here, is what links the input with the output. So the model is just a function. It could be multi-valued. I mean, it could be whatever. It could be something extremely complicated, but I've drawn a straight line. And then you have observations. And because your model is never perfect, the observations never perfectly line up with the model. So your question then is, how do I use my observations to refit a better model? So this is not a difficult question. It's something that you've probably all already done, or at least worked through examples of. You might imagine a root mean square error or a standard linear regression here, but of course it could be in many dimensions and it could be done over different variables. So let's just take an example. How are we going to generate that loss function? Well, let's call the target of our prediction air temperature in Brighton. So that's a seaside resort in the south of the UK for international audiences. And if you are an ice cream seller, say you have an ice cream van and you want to drive your ice cream van down to the seaside to sell ice creams in Brighton, and you have a model and you want to know what the temperature will be in order to know whether you take your ice cream van out or not, then actually, if you're fitting that model, or if you're selecting a model, your loss function or objective function, or the thing that you are minimizing in order to fit this, doesn't actually care at all about the difference between it being -2 degrees and -6 degrees. You have no interest because it's the middle of winter and you're not going to be out selling ice cream anyway. You're interested in what's happening at the top end of the distribution, and maybe you're interested in the difference between 22 degrees and 26 degrees, and maybe that has quite a big impact on your ice cream sales because it changes whether people feel hot enough to buy an ice cream. I don't know. So in principle, you might choose a loss function which is weighted more towards the top end of this domain and prioritizes those observations and those outputs over the ones at the bottom. And maybe it throws away the information at the bottom in service of getting a better fit at the top. Now, suppose instead that you are a civil engineer in Brighton and you are overseeing a project where you're pouring the concrete foundations for a new development. In that case, you don't really care very much about the difference between 22 degrees and 26 degrees, but you care a lot about whether it's going to be below 0, because at freezing, what that means is that your concrete doesn't set properly, it crumbles, you might have to take it up and start again, you've lost a lot of time and you've lost a lot of money. So the civil engineer probably isn't interested in fitting the top end of the distribution, and they're probably not that interested in the bottom end either, but they are really interested in whether it's going to be above or below 0 and the confidence of being above 0. Because that's ultimately the decision that they're trying to inform. So that loss function will look very different to the ice cream sellers. And then just to give a third example, supposing you're Public Health England and you run a hospital trust in Brighton and you're interested in predicting the number of hospital beds that will be occupied, then maybe you're interested in admittance due to heat stress on the very hot days, and maybe you're interested in admittance due to falls on ice on the very cold days. But actually you don't see a huge signal in the middle of the distribution because that's just a normal day and there's nothing particularly interesting about the weather happening. So in that case, your loss function that you want to calibrate in order to select or evaluate a model would be prioritizing the two ends of the distribution, and it wouldn't make much difference what's going on in the middle. Okay, so all of that hopefully makes sense, but it's a complicated way of saying that loss functions are utility functions and they imply value judgments. What that means is that, you know, your position and the decision that you're trying to inform, you have made a value judgment about what outcomes are good and what outcomes are bad, whether that's selling more ice cream or not having to re-pour the concrete. Those value judgments do and can and should enter into your choice of mathematical fit when you're constructing your model. And you might say, oh, well, I'm just going to do a standard linear regression. I'm not going to make any value judgments, but that is also a value judgment. You know, that is putting a weight, a clearly defined weight on the importance of different observations, which is different from an alternative choice that you might make. Okay, so if you're in this sort of nice data-driven situation, you are still making value judgments. Now, what happens if you actually don't have that much data, or you're in the situation that I described where you have, you know, you might have underlying conditions changing, or you might be interested in extreme events where there is a much shorter data set available. Then you've just got a bigger challenge to do this evaluation and to do the calibration. So maybe to say briefly then that the appropriate choices of evaluation tools depend on how it is that you think about model error. You know, people have very different ideas in their heads of what it is that they mean when they're talking about the discrepancy between a model in the computer or on the paper or whatever, and reality, which is the thing that's out there that we're interested in. So just to illustrate that, supposing we have a little sketch of reality and we have the little sketch of our model here, these two sort of spiky blobs. If you are a statistician, if you think statistically, then your idea of what model error is, reality minus the model, is probably statistical. You probably say, well, I've got this complicated thing and I've tried to model it as well as I can. And in doing so, I have modeled all of the, in principle, predictable components, and that therefore what's left, we hope, is random residuals, it's random noise. And so we expect that the distribution of our error term will be random noise according to some distribution with some parameters. And that is that's a coherent and defensible position. But I think it's important to see this then from different angles. Supposing you are a dynamical system theorist, then the way that you think about your model is as a dynamical system, probably quite a complex one, depending exactly what we're doing. And reality itself is also a complex dynamical system. So when we subtract one complex dynamical system from another complex dynamical system, what do we get? We get a third complex dynamical system, and probably one that's even more difficult to look at and understand intuitively, because it's comprised of, again, residuals. And so what that might look like in my little sketch here is this kind of weird spiky thing. I'm subtracting the one weird spiky thing from another weird spiky thing, and I get an even more weird looking spiky thing. So that's how you would think about model error if you're a dynamical systems thinker. And you can see that might lead you to analyze your model error in quite a different way. And now taking a third example, let's say you are not a statistician or a dynamical systems theorist. Let's say you are an anthropologist. and you're coming to this and you say, okay, there's reality out there and here's my model. And the model that I choose is essentially arrived at by throwing away the things that I don't think to be important about this situation. And that is essentially a personal judgment. And so the anthropologist would say that the residual, when you subtract model from reality, will be something that is inherently social and political, something that that reflects the blind spots and the biases and the incorrect assumptions of the modeler, as well as the constraints of their modeling environment. So if that's kind of an inability to express certain kinds of relationships in the right mathematical form to be able to model it, for example. And so again, that's a third really very different way of looking at model error that could lead you to interpret your model in quite a different way. Right, so supposing we have a model which is not perfect, so it's going to have an error term. Here's just another illustration of what that means and why it's important. So for a bit of light relief, here are our 7 models, and they are, as you can see, cute and fluffy. I've got 7 cats here. So the question is, if these are the 7 models that I have made of something, unknown object behind a curtain, how can I use this ensemble of models to make inferences about the properties of the unknown object? So I could look at these and I could say, what do my 7 models have in common? That would be a good start. I could use them to construct confidence intervals. I could say there's an uncertainty range here about the color and the length of fur and the types of vocalization, you name it. And that would be interesting, but it would only be telling us about our set of models and not about reality. So in order to find out something about reality, what do? We go out and we make an observation. So here it comes. We go out and we make an observation. Here it is in the bottom of the screen. So that is it looks like a tail, and it's within the range of our observations of the color and the fur length of the 7 cats. So what are we going to do with this observation? Well, let's go back to our models. Maybe we could do a best fit. We could do a model selection and say, basically, we're going to take that observation and pick the one single model that is most reflective of the observation. So that then depends which dimension you check it against, because we have multiple axes here. We have fur length and we have color, and we might get a different answer if we picked a different dimension to choose the best fit model. Or we might say we've got these multiple dimensions and we're going to keep all of the models that are still consistent with our observation. So then maybe we choose to keep 4 out of our 7 because they are all consistent, and we rule out the other 3 for having the wrong color or for being the fur being too short or something. So you can probably see where I'm going here. But the point is that these models, there are many different statistical methods that we can now use, having generated that observation from reality and gone back to our set of models. But we are not able to infer with full confidence what we think reality looks like. Now, actually, I suspect a number of you are a step ahead and you have inferred with full confidence what reality looks like. So I will show you. Here it is. It's a golden retriever. Now, those models, the 7 cats, they are genuinely informative about reality, about the dog. There is a whole host of aspects of those cats that are informative and useful and help us to make better decisions faced with the dog. If you want to decide what to feed it or how to interact with it, or all of that sort of thing, it's pretty good, right? But it's not perfect. A vet that was trained on those 7 cats would probably be able to have a pretty good stab at treating the dog for most of the things that are wrong with it. But what we can't say is that there is any way, a priori, given those set of 7 cats and the observation of the tail of the dog, there isn't a good way to reconstruct from the cats a picture of what the dog looks like without making significant additional expert judgments. Okay, and the variance within that set of models is not necessarily reflective of the uncertainty that we a priori ought to have about the characteristics of the dog, because the dog, we are getting good information, but it's definitely outside the range of the set of cats on a number of different dimensions. Okay, so that's a very non-mathematical criticism of a lot of different mathematical techniques and statistical techniques that are used to make inferences from sets of models. And, just to say that finding the cat that looks most like a dog is not what we're aiming to do. Okay, so this is essentially what I've already said, but in more technical language, we have options of how we deal with multiple models, and they are all possible and they're all things that people do, but we need to always bear in mind that the models are not perfect, and that the set of models that we have, we should not necessarily expect it to be exchangeable with the real system. Now, if we're in the fully data-driven regime, the left-hand side of the spectrum that I showed to begin with, then you can, because you can take enough observations of the dog to be able to refit your models and come up with an ensemble of 7 dogs rather than an ensemble of 7 cats. So that this again is a distinction between the data-driven regime and the more expert judgment-driven regime, the interpolatory versus extrapolatory. On the left-hand side of that spectrum, we can, in principle, construct a set of models that are close enough to being dogs. And on the right-hand side, we're stuck with a set of models that are cats and that are not dogs, and that we have no a priori way to distinguish. Okay, so moving on then, if we are in this sort of cats and dogs situation, how can we make inferences from ensembles of models? We don't just want to say, oh, hold our hands up and say we can't do anything. I think what we need to do here is reframe our sort of the paradigm of how we understand it and how we go forward. So at the moment, many fields would take the approach of saying, okay, we've got a set of models, they all show X, that something will happen, and that gives us more confidence. But I think if you accept my point, then it's clear that that is not a strong evidence that X is the case. It's only a case that we have, it's only evidence that we have a constrained set of models. So what instead we need to know is that there is no plausible model that could show the opposite. So if we go from, instead of trying to find all models that show X, we want to demonstrate that no plausible model could show not X. That would be a much stronger evidence that X is in fact the case. Okay, but what you immediately notice, I expect, is that the word plausible is doing a huge amount of work in this sentence. The word plausible is what everything hinges on. What do we mean by plausible? How are we going to define a plausible model versus an unrealistic model? It's really difficult. That's really challenging. We have to think about what we mean by expertise. Who do we trust? How are we going to construct this model? What kind of models are acceptable models? Do they have to be, thinking about sort of physical models? Do they have to be physics-based? Do they have to conform to the laws of physics? Yes, they probably do. Thinking about more abstract models, or say models of social systems, what level of expertise should qualify the modeler to be able to say that something is plausible versus not plausible? So if you're modeling, I don't know, say you're modeling virus spread in communities, is it the epidemiologist that has the expertise? Is it the virologist that has the expertise? Is it the social worker that has expertise because they're the one that actually knows who talks to who and when? Or is it the landlord of the local pub that has the expertise? What and how do these different forms of expertise about a situation then end up in the model, and who gets to decide socially whether that counts as being plausible or not? So that introduces a whole load of interesting questions about the social context of doing science and doing this sort of science. But I think what's important to say here maybe is that this is not just a function of me introducing this new idea. This is just reframing the way that we think about the model. It was always important who was making the model and how credible they were and what letters they had after their name and which university they went to. But when we reframe it in this way, we can see more explicitly and more transparently why that's the case and why we need to think about it and why we need to, write about it. Yeah, so that's what I've already said. What counts as a plausible model? How do we know? So I wanted to show you a few more generic examples from the larger scale, the right-hand side of the spectrum, the extrapolatory models that are primarily the subject of my book. Hopefully these will also be interesting. So here's an expert. You probably recognize him, especially if you're in the UK. That's Neil Ferguson from Imperial College in London. And he produced this model on the right-hand side, which was very much influential in the early stages of decision-making around the COVID-19 pandemic. So you can see this is sort of March, April 2020, just as things were starting to take off and people were starting to say, we need a lockdown, we need to do something. And so his model was based on an influenza model that he'd put together previously, and was then calibrated according to the data that was available at the time, which was not very much. So the expert creates a model. And in this sketch, the expert has to make a number of expert judgments. When they make the model, they have to decide what to include. They have to decide how to represent it. They have to decide how to tune it, how to evaluate it. And so their expertise and their understanding of the situation is going into the model. But what I want to argue and what I say in the book is that there's also the reverse step, that the model kind of creates the expert. There's a feedback here, because you don't just create the model and then stop and throw it over a fence to the decision maker. Actually, what you do is you go away and you play with it and you think about it and you test your hypotheses and you change things, you tweak it a bit to get a different output. Maybe you try switching one bit of it off and switching another bit on, and you try to make predictions. And those all influence then how it is that you as the expert understand the situation. I mean, that's the point of making the model, right? Is to be able to play with it and experiment with it. So there's this feedback loop, which means that the model and the expert are kind of acting as a system. The model encapsulates the expert judgments of an expert or perhaps a group of experts. That's how it should be treated statistically as well. That's how we should be understanding the model when we come to put models together and try to make inferences about future conditions. So it is not just predicting, because the model, if this is what had turned out, it would have been absolutely catastrophic. The model, putting together this model, allowed a discussion to happen, which prompted policy intervention, which changed the outcome. So the model is part of the system. But who decides what judgments are represented? Who decides what is politically feasible? When the politician comes and says, I'd really like to know what the impact will be of closing schools, but maybe they don't ask about other kinds of interventions, then you can sort of argue, and people have, about how those value judgments are embedded within models, representations, and visualizations, and then influence the politics. So very briefly, this is a second example of essentially the same point, that we have on the left-hand side 6 alternative models for a baseline energy policy scenario where we continue to use fossil fuels, and on the right-hand side a scenario where we meet the Paris targets by phasing down fossil fuels and ramping up renewables. But you can see that these 6 different models, which are essentially doing the same thing, they have quite different outputs because they make different assumptions. So we have the same question again arising about how who it is that is making the decision about what is plausible in future, whether that's the increase of the price of fossil fuels due to policy, or whether that's the decreasing price of solar energy due to improvements in technology. All of that goes in there. Somebody's making that judgment. Somebody's also deciding what kinds of energy policy are plausible and what are not. And that influences the output you get. And then that output goes back to the decision makers to inform their policies in future. So these models are incredibly powerful. You know, they are changing decisions that influence millions, if not billions of people. And they could really do with more criticism and transparency about the degree to which these assumptions are built in. I could say a lot more about that one, but I won't. But if anybody wants to ask about it, do. So the mathematical challenges then, I think, for decision relevant modeling, the first challenge is escaping from model land. And that means understanding that the world within the model is not the same as the world outside the model, and not just understanding it kind of on that basis, but also propagating that through to the mathematical techniques that we use to analyze these models, because too many of our analytical techniques are based on assumptions which imply that reality is one of our candidate set of models. And if you are confident that you're right at the end of the spectrum in the fully data-driven regime, then perhaps that's okay. But if you're not sure, or if you think you might be somewhere in the middle, then it is something that really bears consideration. And in that case, then we have to think really carefully about the relationship between model and expert judgment. And we have to acknowledge that there is significant social and political content to our models. And so how do we deal with that? Well, it's International Women's Day, so I'm going to make my key point about diversity. So one of the things that we need to do is improve the diversity of our models by pushing the boundaries of models as far as we can, you know, exploring what is plausible and what plausible means to different people with different understanding of the situation and different experience of what's relevant. And if we can do that, and it's not easy, you know, this is a challenging thing to do and to incorporate into the way that science works. If we can push our models out by incorporating more social diversity, then we will get better understanding of the uncertainty ranges that we ought to have, and hopefully also encourage a better relationship between science and society. You know, there are strong groups at the moment who are very anti-science, thinking of like vaccine skeptics, also climate skeptics, and people who sort of a priori distrust anything that is said by large-scale organizations and governments and scientific institutions. But in order to bring those people in and help them to understand the benefits of modeling, they have to be genuinely consulted and genuinely listened to in terms of bringing their understanding and their experience into the model. Otherwise, it won't be credible to them. So can we do that? I think that's a really interesting challenge. But we also don't want to throw the baby out with the bathwater. So I've shown you a number of critiques of large and complex models and forward predictions, and of course that might be attractive to some in this anti-science brigade. And I think that is a risk, that if there is oversell of what science can do in these extrapolatory regimes, and if there is too much of a tendency to obscure the social and political content of models, then there will be a lack of confidence in science. And this is partly what's already happening, I think. So we need to work out a way to be more transparent about the use of these models and be more democratic in the way that they're generated. And then we will have useful scientific information without undermining that confidence. So yeah, just a couple of points to finish then. I mean, the bad news is that unless we are fully data-driven and at the far left-hand side, where we expect the future to be perfectly represented by the statistics of the past, if we're not in that, then we have radical uncertainty of possible future events, and we simply can't expect to be able to fully model it and fully constrain it. There will always be a model risk, and there will always be a gap between model land and real world, which may have cascading consequences when it's discovered. So the global financial crisis in 2008 was essentially a collapse of that form, where the model, the discrepancy between the model and the real became too large, and reality always wins. So we have to do something about this. It has massive consequences if we fail to do something about it. But the good news is that models, because they're not just there to represent and predict, they're also here to change the world. We make models because we want to intervene on the system of interest, and we want to be able to change it, and we want to be able to change it for the better. Better obviously is a value judgment, so we need to talk about what we mean by that. But we can look at our models, we can scrutinize the value judgments that go into them, and we can change them if we don't agree with them. So I think that there's a strong positive message here that, that models are difficult beasts to get to grips with, but that if we do it well, we can use models and we can develop new statistical methods that can support us to make positive and inclusive decisions about a whole range of future policies and actions that affect everybody. So that's, I think, a big opportunity as well as a challenge. And I'll stop there. Thank you.
Thank you so much, Erica. That was super interesting, and I am happy to open the Q&A floor. If you guys want to leave questions in the chat, that's also fine. But if you want to ask out loud, that's great as well. So yeah. Maybe I will use the the opportunity since I am hosting. So I had this question. So basically, we just need to embrace the fact that if we using different models, we're getting different results because the approach to these different models can be different, and we can be coming out from different assumptions, we can have like just different measures of which models are good or bad, plausible or not plausible. But then like how and that's kind of understandable from the statistical perspective as well, but then does it mean that we really never know the truth, or we kind of making this assumption that the plausible models, or like the ones that we test as like good fit ones, they are the ones which bring us like closer to the reality or the truth, but we still never know the truth because it's in a sense like some approximation that we're basing on some assumptions. Is this enough, like in terms of science? It's a very philosophical question, I don't know, but I'm just curious your thoughts on that. Yes.
Yeah, I mean, I think in principle, many aspects of the future are not predictable, but we happen to agree on some things, so I have pretty high confidence that the sun will rise tomorrow, and so do you, and so does everybody else. But that's a judgment. It could be that it won't. It could be that the laws of physics have been the same up to now, and then tomorrow suddenly the speed of light's going to change and everything goes haywire. But we have very high confidence that that's not the case. We have this hierarchy of things that we socially are really confident in. And so socially, we can kind of agree on this set of foundational assumptions without which we can't make any predictions about the future, and with which we can make predictions. And we have got, you know, a few centuries of evidence that we make really good predictions and they're really useful. And, you know, we sent people to the moon 50 years ago. You know, that's an incredible test of a whole range of physical assumptions and ideas and models. So then the question is, how far down do you go? So there are some things that everybody agrees on, and then there are some things that just nobody could possibly know. And all of our science is sort of in the middle, where some people might agree and other people might not agree. So, you know, if we're interested in vaccine efficacy, you could make two separate models, one based on somebody with a strong prior belief in the expectation that this will work, and also with a trust in the system that generates evidence underlying it, but somebody else coming in with a distrust of the system that generated the evidence and a distrust of the model and the modelers, they would end up making a different judgment about the quality of the output of that model. But I suppose what I'm saying is that that's not unreasonable, and that the only way to get past that is to bring those people into the fold somehow by talking more about the assumptions. So supposing I claim that I'm a mind reader and I can predict the card that you have on your desk and it's the 9 of diamonds, and then you do it again and it's the ace of spades, and I get it right 5 times in a row. You know, is that extremely strong evidence that I'm a mind reader, or is it extremely strong evidence that I'm cheating? You know, if you have the a priori belief in the model, then in a Bayesian sense, every time you see that correct prediction, it will confirm the belief that it's a good model. But if you're suspicious already, then every time you see it, it will just confirm your belief that I'm cheating. So what you need is not further runs of the same model. You need to be able to, you know, come to my office and check that I'm not cheating, or do it in a different room, and you have control of the experimental setup, and then you'd be convinced. And I think the same goes for some of these other more political questions. So I can see a couple of questions in the chat too.
Yes, there is a question. There's 2 questions, and one person asked whether they can ask a question. Yes, of course, go ahead and ask. But maybe Erica, if you can take a question from the chat, like that was before that, just to go in order. Yeah, oh, excuse me.
Model selection plays a key role. How do model ensemble methods fit in here? And is there any recommendations on this? I mean, I guess the recommendation is just to think about what you're doing, and not to just take a method out of a statistics textbook and say, I'm going to apply this. Think about what's being implied by the statistical method. I think that is the key. And there are many different methods, and they will have different underlying assumptions. And it's you know, if you just get it in an R package or something that does it all automatically, then it can be pretty difficult to analyze that and to find out what's actually going on underneath. But so it probably isn't appropriate for everybody to do this. But I think, you know, due diligence wise, if we're going to be making significant decisions based on the output of these kind of models, we need to understand what they are doing and why, and what the assumptions are that are embedded in them. Xinwei Li, do you want to unmute? I don't know if they're there.
Maybe we can go to the next one.
We'll go to the next one, shall we?
And they actually wrote a question in the chat, so you can address it. Like,
okay, well, shall we go to Marcos next? How do you see the movement from big tech and other settings towards data-centric scenarios? Yeah, I mean, I'm worried about it. I think that that actually we are moving further towards model land and further into model land, and not on the assumption that we're at the far left-hand side of this spectrum, and that we can take the purely data-driven approaches, and just sort of throwing away and ignoring all of these questions about value judgments and about alternative possibilities. Yes, I think that there's a huge risk in this of people assuming that their model is perfect, either by explicitly stating that or by what they do with the model that implies that judgment. And I suppose one of the aims of my book is to try to generate more discussion about model land and about the difficulties when you're there, and about how we get out of model land, because we always have to get out of model land. If you want to do something in the real world, we always have to get out of model land. So if you just take your model and apply it, you are getting out of model land by making an implicit expert judgment that your model is perfect. But in most cases, that is obviously wrong. So we can start criticizing on that basis. Yeah.
And we have, I guess, like 2 more questions. Yeah.
Yeah, do you want me to just read them out? So Shinwei asks, we know that we want to compare the models via sharpness subject to calibration. Yeah, okay. What about using scores such as CRPS? So that's the continuous rank probability score. So yes, I mean, there's CRPS, there's the Breyer score, there's log probability score, and then you could go into the information criteria. There are many different ways of scoring, but I suppose this goes back to the point that any choice of score implies a value judgment about the relative importance of different kinds of outcomes, and that will be relative to whatever you hope to use your model for. So, you know, what is the basis of comparison for your models? If you've got 6 different models, you could pick the one that does the best on any given score, but you'll get the cat that looks most like a dog. You don't get a dog. So what is it that you're aiming to do, and how good do you think your models are? You know, you have to be extremely confident in your set of models to want to choose the cat that looks most like a dog. If you're slightly less confident, then it's okay to choose maybe a range of cats that will hopefully produce a confidence interval for your dog. Then there are other methods that perhaps put a discrepancy term in and say, we will take a range of cats and they will essentially generate a fuzzy picture of the dog because we'll add noise to everything, or we'll take a range. But regardless of what score you use to do that, you still have the fundamental problem of the potential mismatch between model and reality. So if you are completely data-driven, then you're sort of okay, and it probably won't make much difference which skill score you choose to use, whether that's CRPS or Breyer or a log likelihood. You probably get more or less the same answer. But most of us are not there. And if you're not there, it makes quite a big difference, because, for example, if you use a log likelihood, then you get an infinite probability, you get an infinite penalty for doing something that the model says was impossible. So then that introduces strong dependencies on your choice of scoring function. I mean, there's a huge amount more I could say about that, but I think I'll stop there.
All right. If there is no more questions, there's thank you notes in the chat. We are actually on time, and yeah, if there's no more questions, I'm going to be closing the session. And thanking so much, Erica, for this amazing talk, and congratulations for the book again. Yeah, thank you so much, everyone, for joining us today, and follow our page at Civica Data Science Seminar Series, and we're going to have another seminar in 2 weeks. So thank you, everyone, and we're going to stop the recording.
All right, thank you very much. Good to be here.